because we want to convert the temperature or position or anything analog signal in the world into a digital signal and store them in a computer, because all the computers are digital computers. So why do we need a DAC? We spend so much time and money to convert it to digital signal, and then we have to convert it back. Sometimes, right? Can you think about any applications of using DACs? Audio, yep, that can be. Oscilloscope. It's receiving signals, right? So oscilloscope you used in the lab is actually a big ADC device. So you use a probe to probe any signal on the breadboard. The signal is definitely analog, right? And there's a DAC inside the oscilloscope and convert it into digital signals, and then plot it on the monitor. So they just, for the one you have been using in the lab, it's a digital oscilloscope. So it just plot all the dots to make it looks like an analog signal, but actually it's not. So there's no DAC inside, actually. Yeah. So normally, we need a DACs for actuators, like piezoelectric actuators. If you want to control the actuator using a digital computer, right, you can send digital signals to the actuator, so the actuator can respond with the analog signal after converting to analog. And anywhere else, what about the motors, the DC motors you have been using in microcontrollers? We didn't use DACs, so instead we used PWM, remember? We actually want to control the DC motor using an analog signal, but however, it just takes too many chips, takes too much space on the board. So we didn't actually use a DAC. So what we used is a PWM, just modulate the width of the pulses to decrease the power of the digital output. So in that case, we can reduce the rotation speed of the motor, DC motor, right? So that's, but you can use a DAC to control it, because if you only connect the DC motor to a battery, you can imagine if you give a 5 volts, the rotation speed will be totally different from if you give a 3 volts to the DC motor, right? So that's why you can use a DAC to control it digitally. You just use a microcontroller and write digital signal to the DAC, which is another chip separate from the Arduino microcontroller, right? Just write 110, 001 like that, different digital signals to control the motor with a different speed. So motors are one type of actuator. So there are so many other actuators or robots, right? So you need to convert a digital signal into an analog signal to move something, right? So that's where we need DACs. And there are a couple of companies that are making really good DACs, like Analog Device and Maximum. So all these big companies. And there was a, have you ever heard the .com bubble? When was that? Late 90s, right? When you guys were born by that time. And there was excessive speculations for the internet industry. And people start investing into all these big companies. But 80% of the companies failed within 3 years. So if you look at Intel's stock price per share, back in 2000, it was 50, jumps like $80 per share. And now it's only 50 or something. It's been 20 years. You know that in the US, almost everybody contributes to the stock market because people rely on the stock market to retire for the pensions, right? So if you retire from the company, if you only collect Social Security, only like a little bit more than $1,000 a month. You cannot. It's very hard to survive in the US. So people have to invest into stock market. Can you imagine if somebody rely on Intel 20 years ago and they invested $10,000 in there trying to retire after 20 years? They are still losing money now until now. And I'm not seeing Intel can come back because they are not evolving as quick as possible, or compared to other companies in the world, like TSMC, Taiwan Semiconductor Company, right? So Intel recently has to outsource all the 3-nanometer chips from TSMC. They have their own foundry, but they couldn't make it. They couldn't innovate fast enough to keep up with the technology in the world. So when you are looking for jobs in the future, so look at their stock market first, and then start applying for the job. You know, Intel probably is not a good place to go, but Qualcomm, Broadcom, and NVIDIA, AMD, Micron. You know Micron, making DRAMs in Boise, Idaho, and ASML as well. So ASML is the only company supplying all these lithography machines to TSMC. So you can see there. So TSMC and Samsung are the only two players in the world right now can make 3-nanometer technologies. And for the companies like NVIDIA, AMD, they are making digital chips, ASICs, and they are called fabless companies. In the very beginning, back in the 1980s, 1990s, when people find semiconductors has a bright future in the next 100 years, so they started doing both, like Intel started doing circuit design and fabrication. But you can see right now they couldn't do they are not the best on either side. So they probably are projecting to fail. But after like 10 years or so, they started trying to separate these two businesses in the companies. So the companies are doing digital design, are only doing digital design, like they are called fabless semiconductor companies, like Analog Devices, NVIDIA, AMD, all the companies I was mentioning just now, making CPUs, digital chips, analog chips. So the foundries are just foundries, like TSMC, Global Foundries. There are many others, a couple of really big ones in South Korea as well. So when you are looking for companies, look at their stock market first, right, before you make the decision. So for DACs, like I mentioned, the block, the diagram looks like this. That's a DAC, and it can be, for example, starting from a D, that's one digital bit, right? Dn minus 1, and that's D0 here. So how many bits in total? How many bits in total for the input? N bits. And Vout will be the analog output. So the input is an N bit digital input, like 1 zeros, and output is the analog voltage. And you also need a VREF. So the DAC need a VREF, so it can define the range, the full scale range for all the voltages to be converted into this analog voltage. If this is N bit, so what's the resolution? There's another concept, resolution. It's an N bit. Sometimes you can say it's an N bit resolution, so which means it's a 2 to the nth steps. So it's gonna divide this voltage into 2 to the nth steps, different steps, right? So in that case, there is a concept called the fraction, which is D is a digital input divided by 2 to the nth. So D is the input word. So whatever input is being fed to the DAC. It's called a fraction. And VREF times the fraction, so V out actually equals to VREF, which is the full scale voltage, times F. So if there is a digital signal given, and can you find out the analog output over here? So which will be VREF times D over 2 to the nth, right? Pretty simple. And example, for example, a 3-bit DAC, the input is 100, that's the binary version, and VREF is 5 volts. So what is V out? According, yeah. What is V out? So V out equals to, because totally there are 2 to the nth steps. So the voltage per LSB, 1 LSB equals to how many volts? How many? So the first question, if the DAC is n bit, right? That's the resolution. So every LSB is how many volts? It's going to be, so VREF over 2 to the nth, right? Yeah. Right? You understand this? So V out, because the input is 100, so how many LSBs are there? How many LSBs? 4. Because 1 LSB is this is 1 LSB, right? The least significant bit. This is 1 LSB. So this is 4 LSB. So V out equals to, here's 1 LSB and you have 4. So using this equation, this is actually D times VREF over 2 to the nth, which is 100 times, in the binary form, 5 over 8, which is 4 times, what is this? 0.625? 0.625? Yeah, whatever it is, right? That's the first concept. And second one, the full scale range. Okay, for the input range of a 3-bit DAC, what's the input range for the 3-bit DAC? Input range 000 definitely, to 111. So what's the maximum analog output of a 3-bit DAC? So the maximum output is also called V full scale, VFS, equals to generalized equation. Yes, but if you generalize the equation, this is 2 to the n's minus 1. Do you agree with that? And what's the full range in total? 2 to the n's, right? And times VREF for the n bit. Sorry. That's for the n bit. So the full scale maximum analog voltage is this. So for the 3-bit, it's going to be 7/8 VREF. Is that correct? So it cannot be a VREF. If you have a VREF which is 5 volts, you can never get 5 volts as output. Right, so let's look at one more example. Find the resolution for a DAC if So what you think about this one? I hope the DAC can resolve 1 millivolts. And the reference voltage is 5 volts. What's the resolution should be here? How many bits do you need? So there's an actuator, can be a motor, can be something else, can be a piezoelectric plate, right? And I want to move that actuator using less than 1 millivolts of control. Because 2 millivolts is too much deflection of the actuator. So I want it moves in a minimum of 1 millivolts. And I have a reference voltage with 5 volts. So how many bits do you need for the DAC? Let's do a calculation here. So how do you list the equation? So the resolution is 1 millivolts, which means if I use 5 volts VREF over 2 to the n's, I should have 1 millivolts at least, right? And so you are calculating n here. And it's 5 volts over 1 millivolts equals to 2 to the n's, which is 5,000. So n equals to what? Log 2 5,000. What is that? And so the result is 12.29 bits. So how many bits do you need for the DAC? 13 bits. Do we have 12.29 bits? You don't have. You only have integers, right? So 13 bits are needed. Okay. One more example. find the number of input combinations and the values for one LSB and the full scale voltage generated for a 3-bit, 8-bit, and a 16-bit DAC. VREF is 5 volts, that's given. So you need to find out the number of combinations of the input values and the values for one LSB and the full scale voltage generated for these 3 different types of DACs. We can make a little table because these are the 3 types of DACs and they are the resolution of the DACs. Three-bit, 8-bit, and 16-bit, and you need to find out the number of input combinations and the voltage for one LSB, and also VFS. What is VFS? The full scale voltage. So what is how many combinations for the input for 3-bit? 2 to the 3rd, right? Which is 8. 2 to the 8th, which is 256. 2 to the 16th, which is 65536. What is one LSB? The voltage for one LSB. It's 5 over 8. 5 over this, right? Which is 0.625 volts. This is 5 over 256, which is, you can calculate it. And 5 over this, 25536. You can calculate the voltage by yourself. All right. What about the full scale voltage? So for this one, it's going to be 7 over 8 times 5. This is, what is this? 255 over 256 times 5. And this will be 65535 over 65536 times 5. All right. So the DACs and ADCs are covered in this textbook. So if you want to read for more information, you can read it. This chapter 28, data converter fundamentals. We'll cover the important concepts you need to know. And these are the printed page from the textbook, and these are concepts you need to know in order to do the homework assignments, right? So the first one is called DNL. So we are trying to evaluate the quality or the performance of the DACs or ADCs. You want to know the DNL or INL, gain error, offset error, all these kind of things. So for example, if we take a look at this website, so this one, if you look at introduction, so they will let you know their students have made an ADC, right, in their lab, and the maximum value of NL and DNL is this, right? So that's most important parameters to evaluate the DAC. So the power consumption is something else, it's just power. But for the performance, it's actually NL and DNL. So what are NL and DNLs? That's what you need to know before you start using that ADC or DAC. So let's look at DNL first. Starting from here, differential nonlinearity. That's for the DNL parameter for the DAC. And it's defined as the actual increment height of the transition n, at the nth bit, right? So at that transition, minus the ideal increment height. So before we turn to the next page, so do you know or what you think about the ideal increment height every time of DAC? What's the ideal increment height of the DAC every time? Is it able to increase by 0.5 LSB every time? Is it able to increase by 0.5 LSB every time? No, it has to be 1 LSB every time because that's the resolution. Started from, so the input signal, if you look at the diagram, the input are 1 and zeros. So how can I get a 0.5 LSB? No, the minimum increment will be 1. So it's every step will be 1. So it's going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, like that, every increment. But however, sometimes because of the imperfection of the design, you cannot get 1 LSB increment height every time. So that's where you can get a nonlinearity, a differential nonlinearity as a parameter. And it's evaluated for each bit, for each transition. It's not an overall DNL, is what, like, you can get an average for the overall performance we just saw on the website. It's average performance for all the transitions, but you can evaluate every single transition for all the transitions, all the bits. So if you look at this example here, input, output makes sense. Input are digital signals. Output are all these analog signals. And every change on the x-axis is supposed to get 1 LSB change of the voltage. See, here to here, you get 1 LSB step. So this dashed line is an ideal transition line. Here are all these transitions. And you can see that this is great. This works really well. But here, the transition here is a bit larger than the ideal transition step. So in that case, this is DNL0, DNL1. So all of these DNLs are zeros because there's no errors, nonlinearity. DNL0 is 0, DNL1 is 0, DNL2 is 0, because it's perfect. And DNL3 is not 0. So what is that value? It is 1.5 LSB. And by definition, you want to use this actual step height minus the ideal step. So the actual increment height minus the ideal increment height. So you want to use what? Which to minus which for this single step. So the DNL here, you have a DNL3 will be 1.5 LSB minus 1 LSB, which is 0.5 LSB. So that's the DNL for this transition. So for DNLs, it's always using the actual step height minus the ideal step height, which is 1 LSB. So keep in mind, when you are doing calculating DNLs, just minus 1 LSB always, right? Whatever you have and minus 1 LSB. So let's look at this. DNL3 equals to 1.5 LSB minus 1 LSB, which is this. That's the DNL for the transition 3. What about this guy here? That's the DNL4, right? DNL4 is only 0.5 for the actual height, right? Although it is right at the ideal curve, but by definition, there's a DNL. So the DNL will be 0.5 LSB minus 1 LSB is minus 0.5 LSB. This one, that's DNL5. It's 0.25 LSB minus 1 LSB, which is negative 0.75 LSB. That's DNL5. Here is 1.75 LSB minus 1 LSB, which is 0.75 LSB for DNL6. And here's the ideal height. So there's nothing wrong with this guy. So you can see all these listed calculations for all the DNLs. What about integral nonlinearity? That's another parameter we're going to look at. Integral nonlinearity. So it is actually the difference between the actual output value for the input code minus the output value of the reference line at that point. So the reference line is actually this ideal line. So here's the actual point. So use this actual value minus the ideal point. So what's the difference between NL and DNL? So this is using this point minus the ideal height at every transition as INL, integral nonlinearity. Is that the same as DNL? Step height. Yeah, so something like this point, there's no NL, but there's a DNL. So the point is right at the ideal curve. So NL is 0. But DNL is not 0 because the step is mirroring the step compared to the 1 LSB. However, the NL integral nonlinearity compares the actual value here, the y-axis value, the difference between this y-axis value and the ideal y-axis value. Look at one example, see how that's calculated. All these points, digital input, analog output. NL is 0. NL here is 0.5 LSB. Use the actual value minus whatever it should be on the ideal curve. This is 0, and this will be 0.5 LSB as well. And this is negative 0.75 LSB. Right. Is that clear? Any questions? No. Okay. Offset. There are two different offsets. One is offset error, one is gain error. So we just need to understand it qualitatively, not quantitatively. So this one articulates offset error. So this point should be right at 0, but actually it's not. There's a little offset at the very beginning. So for the voltage, but however the gain error is the slope of the transition curve compared to the ideal curve. That's a gain error. There's nothing to calculate, but just need to know what is that. And now we have a R2R DAC, which is a really simple DAC form or circuit that we're going to use for the lab 2 and lab 3. Let's take a look at the structure. They are both ideal IDC and DACs for lab 2. You directly use. So the purpose for the lab 2 is just to let you guys set up electric and LT-SPICE to let them communicate between each other and also run some simulations. You're not actually designing a DAC and ADC. So these two guys are ideal DAC and ADCs. I just used switches and ideal op-amps to build them, just do a simulation. And in the third lab, we're going to replace this ideal DAC with a whatever we're going to cover today, the R2R ladders, and see if we can get the same result. So V in is a continuous signal, which is an analog signal, and V out will be something like this. Why is that? So look at this curve. Discrete signals, yeah. So this is a ADC. So use the ADC to digitize the analog input first. So you are going to get a 10-bit digital signal for every single point. And after that, you feed all these digital signals into this DAC. So the DAC is going to convert all these digital signals into discrete signals. It cannot be really super smooth because you have a limited resolution, which is a 10-bit resolution. So you are going to see steps instead of a continuous signal. If you increase the resolution to like 14 bits, probably you are not able to see all these little steps. But now because you have a limited resolution, you're going to see all these little steps. Right? So if you increase the resolution, you can smooth out this output signal. Okay. So if you do not have a higher resolution, but you still want a smoother signal output, what you can do? Low-pass filters. So what is a low-pass filter? Capacitor and resistor. It's RC circuit. Why you can see a smoother signal using RC circuit intuitively, not doing the calculations. I hate doing calculations, and I hate when you are doing a lot of calculation and you don't know what's going on. Just calculate it. Write the whole board with all these integral differential functions, but you don't know what's going on there. Just do the calculation, pass the class. That's not working. So intuitively, why a capacitor, RC circuit, since you did RC delay yesterday, right? So why RC delay can smooth out the signal? Why? So keep in mind, remember you used a very sharp edge, right, for the input for the RC circuit yesterday. Remember? So the input is really steep edge. The time delay is pretty much 0. Like you can set up 1 picosecond. But however, you are going to get something like this. So you can calculate the time delay. Is that smoother compared to the sharp edge? It is, right? So because it takes time to charge up the cut. So you can imagine if you have a low pass filter, all these sharp angles, the sharp steps will be smoothed out. Will look smoother, right? So that's why it happens. And so what's the problem though? If you have a low pass filter involved, so it can smooth out the signal, but however, what's going to happen? Slower response. So we got a time delay, and maybe a signal attenuation as well. So these are the issues by involving filters. But it can amplify the signal back to the normal range. But still have a lot of, you are going to introduce time delay to the signal, right? Okay. Okay, so that's what you are going to do next Tuesday. And now let's take a look at why it works, right? So what's the theory behind it? So it's a R2R ladder. Still have time. So there are tons of different types of DACs. During the interview, do not just say R2R ladder is the only DAC available in there. There are many types of DACs, but it's kind of surprising, you know. Just use a string, resistor string, and you can form a DAC really nicely. You know. Topology. So I have around here 2R. 1, 2, 3. Another one. That's the output of the DAC. And this is 2R, 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 2R. So R, R, R. So that's a digital input, D0, D1, D2, D3. How do you analyze this circuit? Why is this doing the job? So 7 is superposition actually need to apply to this circuit. Why? So these are the input signals, right? Input signals, input digital signals, 1 or zeros. So 1, if we use a 5 volts as a VREF, then 1 represents 5 volts. 0 represents ground. So you are actually connecting a 5 volts battery or ground to these digits to make up a digital signal input, right? And you are supposed to get digital signal, analog signal output. So for example, let's pick up the easiest one, right? So what if D0 equals to VDD, which is 5 volts, for example, and D1 equals to D2 equals to D3, which is 0, grounded, just ground them. And what's going to happen? So if you look at circuit, what's going to happen for this case? So if you just look at this part, it's actually connecting a VDD to here, right? It's going to be a VDD 2R, 2R. So what's the voltage here will be? So this is equivalent to what? A voltage divider, right? 2R, 2R. That's VDD, and here will be VDD over 2. Okay. So all the other ones are grounded, but only here you got a VDD, and you need a Stephans equivalent to convert this part into an equivalent circuit. So let's look backwards first. So if you treat everything in that direction as a load, for example, just convert whatever here into its Stephans equivalent circuit, what that looks like. What is RTH? What is RTH here? R. Is that R to R? What is RTH? So that's the load. So these two guys are in parallel. RTH is R. ETH is VDD over 2. So it's actually and this. Is that correct? No. So we just take everything behind this point as a load. So it's actually this, right? VDD, 2R ground, and here is the load. VDD, 2R ground, load. That's a black box, whatever behind it. So when you are doing the Thevenin's equivalent circuit analysis, so one entire lab yesterday is still not enough to let you be familiar with Thevenin's equivalent. No worries, it's not hard. Just watch the videos and it shouldn't be difficult. So that's the circuit. You can convert it into the Thevenin's equivalent, and here's a load, which is going to be VDD over 2, which is a ETH, because that's a voltage divider. And RTH will be, you look backwards, and it's going to be R. All right. So what's going to happen here is you are going to have this one instead of this part, whatever in the red circle here. This guy can replace whatever in here. So you are going to have this VDD over 2 R. See, another R here, another R behind it. And then 2R, R, 2R, R, 2R. D1, D2, D3. And combine this together, you get another 2R. Then what? What's the next? You can do the very similar conversion here. Just follow the same procedure. Is that similar? See, a voltage with 2R, and now you have a voltage 2R, and all these are grounded. D1 is grounded because you are at the very beginning, we are assuming that D0 is VDD, and all the other inputs are grounded. So now you are going to have something like the following. It's if you just look at this part, and treat whatever behind is a load, and do another Thevenin's equivalent circuit. So that will be, that's the original circuit. 2R, 2R, grounded, because this 2R is this 2R. It's grounded. This 2R is this 2R. And here's a load, whatever in the black box. And then convert this guy to VDD over 4 and RTH. Here's a load. RTH is what? Still R. Looking backwards, you short this guy. These two in parallel, it is still R, but this becomes VDD over 4. So you can use this one to replace whatever in here. because that's the Stephans equivalent circuit. And what's next? Keep doing this. So after this, you are going to see something like VDD over 4. That's R. Get another R, which is here. So that R is this R. And then 2R, R, that's T2. T3, that's the input to the op-amp. Still 2R. And keep doing that. So this entire thing here can be converted into something like what? V over 8. Close, right? Is this grounded? Yes, it's grounded, since I assume this is grounded. Why I can assume it? Why I can assume it's grounded? There are so many combinations. 4 bits, how many combinations? 16. 2 to the 4th, right? But why can I assume? Why can I assume these other ones are grounded, but only this one is contributing, right? Superposition. So that's just one example. So I'm gonna, after we have done this, we are going to look at other combinations. It's gonna work for all these cases. So if you look at here, this guy I labeled as D0 because it's 1 LSB, and now let's take a look if it is 1 LSB contributing to it. So since I have a R2R ladder here, why I know that this bit here is LSB. Why is this is MSB? Why not? Why is not here is not MSB? Here is LSB. Why is it the other way around? Because it's keep being divided. It's getting smaller and smaller until it reaches 1 LSB. So now let's take a look at this one. We have an op-amp, but we don't have to have an op-amp over here. Have op-amp, we have to modify the gain in order to make this guy into a VDD over 16 because we have 4 bits, right? So it should be VDD over 16, but no, it's not VDD over 16 yet. So here are some issues for this structure. So you haven't learned op-amp, just remember whatever is happening here. So for the op-amp, they learn it, they already forget everything, so doesn't matter. Elliot is a high school senior. I mean, pretty surprising, right? He's doing a 300 level class, college class right now. Operational amplifiers amplifying signals amplifies because this is plus, this is minus, 2 terminals as inputs and 1 as output. So this is called VP, this is VM. So amplifies VP minus VM times the gain, right, equals to VL. However, if I do not have any feedback, then the open loop gain of the op-amp is infinite, right? So that's why we can form a comparator for using op-amp. But now there's one of the properties for the op-amp, which is if I have a feedback, it's a negative feedback, then the 2 ports are equal. The 2 ports are equal. If you forgot why, just remember it right now. It takes another week to explain why. Right? So they are equal, virtually equal to each other. That's why you can amplify a signal with a modified gain, not an infinite gain. So if this is grounded, this is virtually grounded as well. $11.10 or $11.5. Okay. All right. We should do this on Wednesday though. I will see you next time. I saw it's 15. So. Okay. All right, we'll do it next time.